So now let us start. Hello everyone, welcome to the second day of the workshop. So today we are going to discuss new laboratory proofs on Axion-Like particles. So you are basically allowed to interrupt during the talk, and only if there are too many interruptions, then I may intervene. So as the first speaker, we are happy to have Tomohiro from University of Tokyo. So he's going to tell us laser experiments and protoplanetary disk for hunting out dark matter. So please.
Thank you very much. Thank you very much for inviting me. So today I'd like to talk about a new way to search for Axion-Like dark matter using laser experiments and the observation of protoplanetary disks. So again, I'm Tomohiro Fujita from Tokyo University. This talk is based on 3 papers published in PLL this couple of years. Okay, let's get started. So let's start with introduction. So the question is, who is dark matter, or what is dark matter? And as you may know, there are many dark matter candidates. So the leading example, like a leading candidate is WIMP type dark matter, but we have a bunch of different other candidates like a neutrino, stellar neutrino, primordial black hole, modified gravity, and scalar type dark matter. So today's talk, I like to focus on this scalar type dark matter. And the scalar type dark matter is quite different from particle, so WIMP type dark matter. So if you solve the equation motion for scalar type dark matter, you find the solution is oscillating scalar field once mass is bigger than Hubble. So solution is given like this. So this phi scalar field is oscillating around its potential, mass potential. I propose some later animation here. So it's oscillating around its mass potential. Also, its amplitude decays as cosmic expansion. It decays due to cosmic expansion, but I will ignore this cosmic expansion later. Anyway, so this is the basic stuff of scalar type dark matter. And on top of that, when I specify Axion-Like dark matter or Axion-Like matter, that means I assume following three properties. One is Axion-Like dark matter can be very light due to cis symmetry. It can be as light as 10 to the minus 22 electron volt. The second property is Axion-Like dark matter breaks the polity symmetry. So since axion is shooter scalar field, when it's involved in the physics, the system differentiates left-handed mode and the right-handed mode. So polity is broken. And the third one, and the most important one, is axion may be coupled to gauge field, including photon. So if it's coupled to photon, it's very advantageous to us in terms of searching or discovery, because we can use advanced technology of optics or observational techniques in astrophysics. So it's a third property. So I assume all of them in this talk. And regarding axion-photon coupling, so in Lagrangian, interaction term is written like this, so-called Chern-Simon term. So this G is coupling constant in the unit of GB inverse, and phi is axion, and F is normal field strength of photon, and F tilde is its dual. So you can immediately write down the equation motion for photon and axion, and the left-hand side is just a normal wave equation for gauge potential, vector potential, and for axion, it's a normal Klein-Golden equation, but you got the additional term on the right-hand side due to this interaction term. And the one thing you immediately notice is we have rotation of vector potential, which is nothing but magnetic field. So conventionally, people try using this additional term by applying magnetic field in experiment. So let's assume constant magnetic field, which is maybe you can apply magnetic field by yourself. Then, so the rotation of vector potential in the previous page is replaced by B naught here, amplitude of magnetic field, your magnetic field. So if, for example, this equation means so photon get the source term proportional to coupling constant and amplitude of your magnetic field and the dot time derivative of your axion. So this equation means if propagating axion enters a region with magnetic field, so photon gets the source term. So photon is amplified, photon is produced. So this phenomena is called axion photon conversion. And the opposite reaction also happens. So photon can convert it into axion. So axion photon conversion. It's kind of famous. So this gigantic experiment called CAST experiment at CERN try to use this axion photon conversion. So their idea is rather simple. So we expect some axions are produced inside the sun, our sun in the solar system, and some of them are flying to us. So what we want to do is applying magnetic field here inside this experimental facility, and waiting for axion, it gets converted into photon due to this magnetic field. Once it's become photon, by using X-ray detector, we can detect photon. Okay. So this type of experiment is called axion helioscope. And this is an important plot. So x-axis is axion mass, the unit of electron volt. So here is 1 electron volt, and here is 10 to the minus 22 electron volt, lower bound for axion-like dark matter. And the y-axis is coupling constant between photon and axion in the unit of GV inverse. So this blue shaded region is already excluded by CAST experiment, which I just explained. Here is already excluded. And additionally, so several astronomical observation also kills this region, parameter region. So they achieved a little bit better sensitivity than CAST. So this is the current situation, and we also have a ADMX experiment here. And this yellow band is a QCD axion line. But in this talk, so this empty region, we have a big empty region here. This is our target parameter space in our project. So it's deviated from QCD axion, so it's axion-like particle type, axion-like particle parameter space. But we may have dark matter somewhere in this empty region. Okay. So come back to this equation, and let's consider another way to use this source, like this additional term coming from the interaction Lagrangian. Anything other than magnetic field. So another assumption is, what if axion is dark matter? So let's assume dark matter is axion. And for simplicity, in this talk I assume 100% of dark matter is axion or axion-like particle, which has a photon coupling. In that case, as I explained at the beginning of my talk, so we know the behavior of axion-like dark matter. So it's oscillating around its mass potential. So we can plug this behavior into this equation of motion for photon. Then this equation motion become a linear order of photon vector potential here. So then using left and right-handed polarization or circular polarization decomposition, so this equation motion for photon can be related or translated into dispersion relation of photon for left-handed mode and right-handed mode. This is it. So normally normal dispersion relation for photon is nothing but omega square equals to k square, of course. So I use the natural unit, so c square is hidden here. But due to axion photon coupling, we have a collection term here. You see? So collection term proportional to coupling constant, oscillating amplitude, and mass divided by so k, fluid mode, and the psi mt. So this equation means, so speed of light changes depending on polarization. So I forgot to say that this flipped sign corresponds to left-handed and right-handed mode of photon. So sometimes, okay, and this time, the sign of this time also flips due to this sign factor. Always sign becomes plus or minus. It's oscillating. So sometimes,
if we consider the just linear polarization.
So say again.
What happens if we just considered linear polarization rather than this circular polarization?
In that case, you cannot write in this way. So it's because the tricky part is you have a epsilon ijk here. So we have a rotation. So you need to use this circular polarization to write down this kind of like a simple way. Of course, you always decompose. And in the few slides, I will explain what happened to the linear polarization. This is Okay, next slide. I will discuss about linear polarization. But first, I think it's easier to understand in the language of circular polarization. Is it okay?
Yeah. Go ahead.
Okay, so if you decompose photon by using circular polarization, that means left-handed mode and the right-handed mode have a different speed, and which is faster always changes due to this oscillating behavior of the axion dark matter. Okay, that is the end of introduction. Is there any other question? Otherwise, I move forward to circular linear polarization.
I have a question in the previous slide.
Yes.
Yes. So you said the speed of light change depending on polarization. So
yes.
The question is, so there is some group velocity and phase velocity. Both some difference are important, or for example, phase velocity difference is more important, or whatever. Yeah.
That's a very good question. So here, phase velocity is important. Phase velocity is important, and phase velocity, the collection to phase velocity is order of g, and if you calculate the collection to group velocity, that is order of g squared. So that's a higher order and very tiny. So that means if you consider a wave bucket of photon, for example, it's like actual propagating speed doesn't change much due to axion. That's a second order collection. So group velocity effect. So here, yeah, so your question is very important. So the phase, so collection to the phase is a key in this birefringence phenomena. So I forgot to say this. So phenomenon is called birefringence.
Okay, thank you.
You're welcome. Okay. If there's no more question, let me go to the second part. Okay, so I already had one question about linear polarization. So let's consider linear polarization photon. So let's assume this guy is photon. So linear polarization photon propagating one direction, let's say along the z direction from time t to t plus capital T. Okay, easy setup. And the initial condition is circular polarization. I suppress z component because I assume photon propagating along the z-axis, and the photon is transverse mode. So z component is always 0. Anyway, so and as we learn in undergrad, the linear polarization always can be always decomposed into circular polarization mode. So in this case, 1/2, so circular polarizations. And then, so as we learned in the previous slide, so these two circular polarizations obtain the different phase velocities, different phase. Of course, we have a common part, but some different part has an opposite sign. Okay, so during this trouble, so both mode, left-handed mode and right-handed mode, obtain some phase here, and this collection due to axion, this additional part has a flipped sign, as we'll see in the dispersion relation. And at the end of the day, you combine these two contributions and you get this result, cosine and sine. This means you start with linear polarization. Okay, I will show you animation in the next slide. Okay, here's our animation. Look at here. So without axion in the vacuum, so photon just propagating linear polarized photon looks like this, just a linear polarization. But if you turn on axion photon coupling and the axion, and of course I made an assumption that the axion is dark matter, so it's oscillating around its potential. Then, so what happened is, so this linear polarization plane is gradually rotates. So it's interesting. And this rotation of polarization plane is in phase with this oscillation of axion field around its mass potential. Okay, so you can imagine that so normal case, so two circular polarization has the same speed, Then if you combine these two circular polarizations, it's just a linear motion. But if okay, my right hand motion is a little bit faster than left hand. It's hard to do that, but you can imagine that. Then you can imagine like this linear polarization rotation plane is gradually, slowly rotates. I hope you can imagine that. And of course, you can do some mathematics. You can do some calculation. You get some result. Interestingly, so since this collection of the collection to dispersion relation is proportional to time derivative of axion, and you want to integrate over this phase over the time, so result only depends on boundary time. So at the point of emission and at the point of observation. So it doesn't matter what happened in between the observation and the emission point. That is another property, but this is not very important current discussion. Anyways, so we expect some rotation of linear polarization plane due to Axion-Like dark matter. Okay, so it can be a smoking gun of Axion-Like dark matter. So let's do some order estimate of this rotation angle, theta. And if you plug some number, okay, so allowed coupling constant, maximum value is 10 to the minus 12 GeV inverse. And in this case, lower mass is better. So let's plug 10 to the minus 22 electron volt. In that case, theta could be 10 to the minus 2. So it's not so tiny. So in astronomical observation, we can detect such a rotation of polarization angle. However, here's a problem, one problem. So to measure this rotation, like a rotation angle of polarization plane, you need to know both initial polarization plane and the final polarization plane. It's easier to know final polarization plane because you observe the photon. But in astronomical observation, it's generally difficult to know initial polarization plane. That was a bit tricky part.
Can I ask a question?
Yes.
So far, you assume that the axion field oscillates coherently everywhere. But so what happens if you take into account the realization and the coherence?
That's also a very good question. And I didn't assume axion is coherent everywhere. You don't need to assume that. But I assume
in the formula you wrote sine of mt, right? For the oscillation.
Sorry?
So if you go back to the formula you wrote, let's say the final one, for example.
Which one?
Yeah, so I see sine of m times t. M is the mass, the frequency. On the other hand, the frequency is not monochromatic, right? Because of the realization, the frequency oscillates with time.
Yeah, I know what you mean. I know. So in other words, so here, okay. Here I should plug, this is, so the rotation angle actually depends on the axion field value at the emission point and the detection point or observation point. And if the distance between observation point and emission point are far, larger than coherent length of axion inside the galaxy, okay, my target of observational target is inside our galaxy, so it's not so far away. But anyway, so the distance is larger than coherent patch. Then, so this theta, this guy and this guy oscillate in the different phase. You are right. Yeah, but that doesn't change the discussion much. In the paper, we took into account that effect, but it doesn't matter because so it's cosine and it's cosine. Even if they have a different phase, it's just the result is cosine. It's a combination of just addition of cosine.
Okay.
Yeah. Thank you very much. But that's also a good point. And okay, anyway, so our problem was, so we want to know the initial polarization angle. So then, we found the protoplanetary disk. Probably you are not so familiar with it, and I wasn't so familiar with it. But anyway, so this protoplanetary disk is, okay, this is a real data and it's an image, but the flat and gaseous object surrounding a young star. So imagine that when sun was born, and it's the sun, our sun, and the planet were not yet formed. But before having a planet, we had this kind of dust disk around the young sun, and that is true for other exoplanets. So, and this disk, simply by scattering a central star light, they shine. So they're bright. So PPD, let's call it protoplanetary disk. It's called PPDs. Are bright simply by scattering a central star's light. So the light coming from this disk is polarized, linearly polarized. You see, so central star emits its photon, and this dust scatters it, and we observe it. So it's polarized. And the simulation, so it's simulation done by my collaborator. So simulation shows that the beautiful concentric pattern of linear polarization is produced at the protoplanetary disk. So now we know the initial pattern of polarization. And we expect that, so during the propagation from this PPD emission point to Earth, so axion birefringence, so dark matter axion, so distorts this concentric pattern into spiral pattern. So it's interesting, right? So all we need to do is just measure this angle theta and ask it's a 90 degree or not. If it's a 90 degree, so there is no axion, and it's deviated from 90 degree, that's probably smoking gun of axion-like dark matter. And it's actual observational data taken by Subaru telescope, and our target is 160 parsec away in our galaxy. So analyze the data. This data, we found that the result is theta is 90.1 plus minus 0.2 degree. So it's consistent with 90 degrees. So we failed to discover axion-like dark matter, but we can put the upper bound. And actually, we achieved the best sensitivity around this mass region. Okay, but I should warn you that the left region is too small. The mass of axion is too small to be a dark matter, but I have already assumed that 100% of dark matter is axion. So this region doesn't it's not reasonable, but in this region we improved the constraint. So this black line is our new constraint. So this is our result, first result coming from polarization plane observation. So in one word, we improved the bound on fuzzy dark matter, whose mass is 10 to the minus 22 electron volt.
What is the mass dependence due to?
Yeah, mass dependence. There are some several places. Mass appears several places, and some cancellation happens. But basically, if mass is smaller, okay, let's explain this way. So if mass is very large, so linear polarization after emission, it like a linear polarization plane moves something like this, oscillates in phase with axion oscillation. And if axion mass is very large, that means axion oscillation is very fast. So the, how to say, amplitude of rotation is very small in that case. If axion mass is small, for example, in the case of 10 to the minus 22 electron volt, the oscillation period of axion is about 1 year, 1.3 year. So it goes either clockwise or counterclockwise for 1 year. So amplitude is bigger for smaller mass. That's the main reason.
Excuse me. As
Yes.
you mentioned, there are some dust around the protoplanetary disk that
Yes.
could also produce the similar effect to axion due to some Compton scattering or something like that. I mean, there are some background effect that can produce similar effect. How could you exclude them?
Similar effect due to
some scattering in the dust.
Okay, yeah, something may happen. Okay, so short answer is, okay, as far as I put the upper bound, that's not the very Okay, that's not a big deal. But if I found some signal, we need to carefully consider some another effect or some another effect than Axion-like dark matter. But at this point, so we just put up a bound. So it's it's not serious. We don't need to be so serious about other effect. Yeah, but I come back to that point in 2 slides, I think.
Okay.
Okay, but before that, I should mention that a couple of months after our paper, another paper appeared, so Federici et al., and they used a very different phenomena. They used the CMB data, and they put another bound on Axion-like dark matter. So again, it's x-axis is mass and y-axis is coupling constant. So this black line I added is our bound, PPD bound, photoplanetary disk bound. But this green shaded region is their improved bound from Planck data. As far as I know, it's the best bounds so far. So they use a very different technique, but this is the current best bound, I think I should mention. Okay. However, so in my previous work, so in this work, it's a bit. So in this work, I used just one snapshot of protoplanetary disk, but so in principle, if we can observe one protoplanetary disk for a very long time, we should be able to observe this kind of time variation. It's correspond to that like a motion of the polarization plane, right? And as I said earlier, so this period is about 1 year. So if I can make, for example, 10 times observation within 1 year, okay, every month, if I can make observation every month, for example, I should observe this kind of behavior of polarization plane, right? So that is a new technique. We haven't yet used that, but that could be the potentially new technique, potentially improve our sensitivity quite a lot. And this is a forecast done by these people, not including myself, although they are in Tokyo University. They're independently do their research. Anyway, so x-axis is again mass and the coupling constant is y-axis. And here is a current best bound. And these people forecasted the potential of different like observational objects. For example, pulsar or AGN jet, and PPD is a protoplanetary disk, and supernova remnants, and CMB-S4. So this is CMB. So they concluded that the protoplanetary disk observation has the biggest potential. So protoplanetary disk may achieve the best sensitivity in the future. So motivated from that, I also doing additional research on this in this direction. Okay, that is first part of my talk.
So this constraint is based on the assumption that the Axion dark matter comprise the whole amount of dark matter.
Exactly, yeah. I assume the 100% of dark matter is Axion.
For the mass region, the relevant mass region, the typical misalignment production may not fulfill the requirement.
Okay. So yeah, we didn't like specify any production mechanism. Yeah, that's quite often asked question. Yeah, that is a big question, that how to produce such a tiny mass, extremely light, people call it ultra light Axion-like particle. That is very, of course, important question. Here I just experimentally or observationally try to detect. Yeah, by assuming such existence of Axion-like dark matter.
So it means a hierarchically larger photon coupling.
Yes. So compared to normal, for example, QCD axion, so coupling constant should be much extremely lower than this region. So yeah, so it's better to have some like a boost mechanism.
Okay.
yeah, in any case, it's a current best bound. So, okay. So then, so I want to go to next section, gravitational wave interferometer. I think it's a lightest part. It's kind of easy. Okay, so looks like a okay. Topic looks like changed completely, but it's not. I will still continue to talk about Axion-Like dark matter, but for a while, let me say a few words about gravitational wave laser interferometers. As you may know, we have a bunch of different gravitational wave observatory in the world, and also in Japan, we are constructing Kagla. It's almost completed. And here the question is, can we use gravitational wave interferometer to search for Axion-Like dark matter? And the answer is yes. Actually, gravitational wave interferometer is ideal for Axion-Like dark matter detection, because it's, first of all, it uses linear polarization laser from the beginning, and they have a very long baseline. In the case of advanced LIGO, it's 4 kilometers. In the case of Kagla, it's 3 kilometers. And the photon reflects many times, typically 500 times. So photon flies, photon travels for a very long distance. And of course, it's a gravitational wave detector. It's designed to detect tiny, tiny signal. So it can achieve very good sensitivity. So this, like a fact, is first pointed out by Delac and Hook. Actually, this guy was the first speaker in this workshop, William. And so after this paper, we consider more realistic setup to use gravitational wave interferometer to search for Axion-Like dark matter. So this time, it's not complicated because we know, so we use our laser, linear polarized laser, so we know the intrinsic direction of the polarized plane. And all we need to do is just filter out the original polarization direction and extract the perpendicular polarization component. Okay, so it's so this component shows up only if Axion dark matter rotates its polarization plane. And the setup is kind of simple. Yeah, all we need to do is just introduce at least one photo detector, either here or there, but it's not very difficult. And the one big advantage is, so this observational strategy or detection strategy coexists with gravitational wave observation. So it doesn't, so our Axion-Like dark matter search doesn't disturb gravitational wave observation. So they can coexist. So that's a very good point. So this is the future sensitivity, projected sensitivity. If we introduce one photo detector in Kagla or advanced LIGO or any other future planned gravitational wave observatory like DSIGO or Cosmic Explorer, we can achieve a really good sensitivity. Yeah, like this. For example, in the case of advanced LIGO, so it's better than CAST by almost 2 orders of magnitude around here. You may notice that there are many spikes here. Why we have these spikes? Because, let me explain. Okay, let's first assume the case mass of the axion is very light. Oh, I forgot to say. So now we are looking at the mass lesion slightly heavier than the previous one. So previously we discussed something like 10 to the minus 22 fuzzy dark matter lesion. Now we move to heavier lesion, but still very light. Okay. But let's consider some light mass lesion. In that case, so oscillation period is very long. So we can consider that, okay, let's say right-handed mode. Right-handed polarization photon is faster than left-handed mode. Okay, let's consider in that case. So then photon start from here and travel to this end mirror. There, so since right-handed mode is faster, so the polarization rotates like this. And the photon gets reflected here and going back. And here's a tricky part. So once you get reflected, but still right-handed mode is faster, so your polarization plane, it's a bit tricky, but consider that. like imagine you're a photon and get reflected, and so your going direction is flipped. Then so polarization, still right-handed polarization is faster, so polarization plane rotates clockwise. Then polarization plane going back to the original position. So the effect is cancelled. This is quite unfortunate, but it's true that so the effect is cancelled. Like, if the always right-handed mode is faster during this round trip movement of one photon. Okay, so best case is, so as I said, so here I wrote the dispersion relation again. So here, this which mode is faster is always flips due to this sign factor. So the best case is the one way, during the one way from like this mirror to end mirror. So right-handed mode is faster. And then when I get flipped here, so the sign changes here, and now left-handed mode gets faster. That's possible if the oscillation period, half of it is the same as this like photon propagation time, one wave photon propagation time. Then left-handed mode gets faster now, and the polarization moves the other direction. Then the rotation is not cancelled. Actually, rotation is added. This is a resonant point. So you should be very lucky to have this effect. So normally you have this cancellation. Okay. So that's why we have huge spikes. At the spike point, we have very good sensitivity, but other than spike point, our sensitivity is much suppressed. Do I make myself understood? So cancellation, huge cancellation happens around here. Please consider like original sensitivity was something like this, but due to this cancellation effect, we have a huge suppression. Okay. But still, okay, it's advantage of this idea is it's cheap. It just introduced one photodetector into existence gravitational wave observatory. So we can easily do that. So we actually plan to do that within 2 years. And I work with Kagura people in Japan. So our plan is we get the world first gravitational wave and the Axion-Like dark matter observatory. And we apply for grant, and I had a rumor it's fast, so it's approved. So we will get some money to do that. Okay, that's the end of the section 3. Actually, this part is going to be a bit important for the next section. Is it okay? Was it clear for you? If so, let me proceed. Yeah. Okay. Bottom line is some cancellation happened due to the reflection. So now finally, optical, let me explain optical link cavity. I was asked to talk about it when I get the invitation. So yes, I show you again the same slide. So in the case of gravitational wave interferometer, so since photon go and back, so just go get flipped. They flipped here, go back and forth. So in many cases, unless you're very lucky, the rotation of polarization plane is canceled out, and you're left with very small, tiny effect. So we want to solve this problem. And the solution is quite simple. The problem is you get the only one reflection here. That's why so you get the cancellation. So if you get the double reflection, this problem is resolved. So now you never cancel the polarization rotation. Okay? You never cancel the loop. And this like a polarization rotation effect is accumulated. So this is our idea. So we just use a linear polarization laser and inject a linear polarization laser photon and go into here, and the photon goes around this ring cavity. This is so-called bow tie optical ring cavity. And during this like travel, photon polarization plane gradually and slowly rotates. So, and at the end of the day, so we extract such a perpendicular component. And that should be the Axion signal. Okay, and it's a projected sensitivity. So here's a cast. So this line is 1 meter size. So 1 meter means, so this travel length is 1 meter. So this size is 50 centimeter. So it's 1 meter size. It's a tabletop experiment. Can achieve a much better sensitivity than CAS, and even better than other astronomical observation constraint. And if I make it 10 meter size and very expensive mirror and a very expensive laser, then I can achieve this kind of very, very good, fantastic sensitivity towards Axion-Like dark matter. This is our proposal. We call it dance experiment. I forgot to say that. Dark matter Axion search with ring cavity experiment. We call it dance. Yes, so we can improve the constraint by several orders of magnitude by tabletop experiment. And some optics people are also interested in this, and Nature Photonics wrote an article about that. And so last year, so let me tell you a few words about the current status of this dance experiment. So last year we got some grant, so we got some money, and started with 1 meter size prototype. So this is it. So again, so 1 meter means this, like a travel length is 1 meter. Okay. So that means this size is 50 centimeter actually. So it's tabletop size. And this year we finished constructing this prototype experiment. We call it Dance Act 1. It's a prototype. So size is 1 meter size, and we use like a cheaper laser, cheaper mirror. So it's not that high sensitivity, but anyway, it's a very nice prototype experiment to do R&D. And the first test result was obtained 2 months ago. And you can see this is the size, and these two PhD students are working on this experiment. And the first test result is this. Of course, okay, sorry, there are some Japanese words here. I got this slide from her, a student working on this experiment. So, but important point is this red dashed line is design sensitivity of the prototype experiment. So we expect to achieve this kind of sensitivity even with this cheap prototype. And this is the current status. So we still about 5 orders of magnitude worse than design sensitivity. So we need to find noise sources and kill them. So that's what we are doing now. Anyway, once we can do that, so once we like hunt all the noises and achieve the design sensitivity, so we will get ready to make it bigger and achieve this kind of sensitivity. So this is a busy plot, but I put everything here. So here's a QC reaction, and these 2 lines, this red dash line is dance act 1, so 1 meter size, and cheaper facilities, and that full size dance, 10 meter size, and better mirror, better laser will be around here. We'll achieve very good sensitivity. And this line, purple dash line, is advanced LIGO. So, gravitational wave detector, gravitational wave interferometer. You can see spikes here. And also you notice that this abracadabra experiment, which is proposed by MIT and other universities. Let me say a few words about that. So abracadabra also.
May I ask you before
yes.
we move?
Yes.
What is the loss in sensitivity at higher axion masses due in the case of dance? Why the best sensitivity is so low in mass?
Okay. Thank you very much. This is mainly because the coherent time. Yeah. So coherence. So if mass is higher, the coherent time of axion gets shorter and shorter. So that means. Okay, let me explain a little bit more. So here, so idealistically, just having a perpendicular polarization component other than the initial one is a Axion signal. But in reality, there are many noises, right? So what we want to do is, okay, we monitor this perpendicular component of polarization vector, and we look for the oscillating behavior of such a component, right? Because the prediction of Axion-Like dark matter is, so we always have this kind of like a perpendicular component, and its amplitude is always oscillating in phase with axion field oscillation. So we always have some signal, like this perpendicular component, axion signal plus noises, and noises expect to be much larger than axion signal. So basically, we will do Fourier transformation and like extract axion contribution, which is supposed to be cosine oscillation. That is a story. However, if the coherent time is very short, so your axion signal is not so cosine, like it's not so beautiful sinusoidal behavior. It always have a jump of phase, like once the Earth goes through each coherent patch of axion, so the axion phase suddenly changes. So that's like a Fourier transformation strategy. It doesn't work well. So you need to cut into the data into small pieces and analyze them independently. That loses the sensitivity much.
And you don't get any resonance effect if you tune in the size of the
yeah, in this case, no. In this case, no. Or please consider that actually this dance experiment is something like we always at the resonance, because this loss, like a loss of sensitivity of like happened in this like a gravitational wave observatory is already like a result. So we don't have this loss of the sensitivity. So we are always around here, in a sense. So that is this sensitivity. But you can see that, okay, let me go back to this gravitational wave. Yes, in this case, if you just look at the resonant point, you also has a loss of sensitivity for higher mass. So it's kind of inevitable.
Okay, thank you.
Thank you.
Then there must be lower bound on this sensitivity of dance, because you said that we have to do Fourier transformation of the signal to reduce to reject the background. And if the XMS is too small, then the oscillation frequency is too short.
You're completely right. You're completely right. Yes, the reason why I cut here is here I assume 1 year experiment, and so this, yeah, so yeah, that's why I cut here. Yeah, I cannot extend this line like to the left unless I do a very long time experiment. Yeah, you're right.
And the sensitivity line basically kind of proportional to the size of detector. If L is much larger than, if it is like 100 meter, then it's improved.
I think sensitivity is just proportional to length. Yes, so if you can make it 100 meter, it's 10 times. It will be 10 times better. Also, please notice I also changed other other parameter. For example, this F is finesse. Basically says how many times photon gets reflected inside cavity. So if it means the quality of mirror. So if photon gets reflected more time by this mirror, so they stay inside this cavity for a longer time and get the more rotation of polarization plane.
Then why don't you consider 100 meter detector?
Yeah, it's very easy to say and draw projected sensitivity for 100 meter. Yeah, I can say that, but yeah, 10 meter. Yeah, I can say that 10 meter or 100 meter, 1 kilometer, up to your ambition and up to your wallet, your money.
So for 100 meter, it can touch the the typical dark matter line?
You mean
I mean, based on the reproduction.
Standard Axion-like particle, like misalignment.
Yeah.
I don't know. I don't think so, because abracadabra, I think it goes parallel to that line. Like say very close to that standard Axion scenario line. So maybe something around here. Sorry, I don't remember well, but I think still dance doesn't touch that line, even if it's 10 times bigger.
Okay.
And so this abracadabra looks so good, and it's basically it's complementary. So the best sensitivity mass region is defined, but I should say still I have the 10 here, but I should quickly go through abracadabra. So current status is, so they have a plan. So this is a full size abracadabra, really like a remarkable sensitivity. But they of course started with a smaller one, 10-meter size. And their original plans, they say, so 10-meter size, even if noise is 100 times bigger than their expectation, so they can achieve a better sensitivity than CAST. This shaded line is CAST. And this is like a basic prediction of 10-meter size abracadabra. And they made it. And but the result is, for some reason I don't know well. So this is a CAST sensitivity line, and this is their result. So their result is not that good as expected, but of course it's an experiment. So you need to make it and check the noise and hunt the noise sources. So you need to do a lot of effort. So the main reason why I said it is we are in the very similar situation that. So we constructed the 50 centimeter size downs, and our current sensitivity is much worse than design sensitivity, but we know how to improve it, and we are working on that. So please, so please stay tuned, and please looking forward to see next talk about it. And of course, there are more attractive proposals. For example, even better way to detect Axion-like dark matter is proposed by these people. So let's looking forward to hearing the next talk. Okay, it's time. Let me summarize my talk. So Axion has been constrained by Axion photon conversion by applying magnetic field like a CAST. That was a normal, a conventional way Axion photon conversion was used. However, the same coupling, Chern-Simon coupling, causes axion birefringence in the case of Axion-like dark matter. If you have a background axion, so photon just have get the influence of the Axion-like dark matter. So, and we propose and actually conducting that optical linked cavity experiment, and in 1 or 2 years, we will introduce actual photodetector into KAGRA, gravitational wave interferometer. And hopefully we achieve a good sensitivity and improve the constraint or discover Axion-like dark matter with this mass region. And at the first part of my talk, I also discuss observation of protoplanetary disks, which is useful to search for ultralight Axion-like dark matter, the most lightest mass region of dark matter, which is 10 to the minus 22 or 10 to the minus 20 electron volt. So, and in this talk I didn't mention, but also CMB birefringence probes Axion-like dark matter, as well as Axion dark energy. So it opens a new window, a new way to provides a new way to search for do new science. Okay, thank you very much. That's it.
Thank you very much for nice talk. So, any further questions or comments? So we will have a, okay, so Takahiro.
Is it also possible to use the PPD observation to constrain the gravitational waves?
I don't think so. PPD observation to gravitational wave. I don't think so. Yeah. It's just, I think the point is we want to see how photon gets influenced by Axion-Like dark matter. And the reason why I could use gravitational wave interferometer is they happen to use photon to detect gravitational wave. But they don't have to. Like there are, for example, there are like a torsion balance experiment is also sensitive to gravitational wave. So yeah, and the gravitational, yeah, I don't see any good connection between that protoplanetary disk and the gravitational wave. So I don't, yeah, I don't immediately come up with a good idea.
I see.
So yeah, in the same plot you showed not this one, maybe previous one. Yeah, this one. So in the right part of the figure, they shows all same deficit angle or some rotation angle. Is it? I mean,
So-
compared to in the I mean in the previous slide. So compared to left plot, in the right plot, they shows all same directional. I mean, change. And I mean, so angles theta are all same for all direction. So compared to 90°, is it just a simplification or?
So here, okay, in this plot, sorry, I didn't completely get the question, but so let me explain this slide. So here, the prediction of this scattering mechanism, so simulation of production of this polarization plane, polarization pattern, say, okay, basically this originally at the position of protoplanetary disk, this theta, for any photon. So you can define theta for every photon, and the theta expected to 90° originally.
Yeah.
However, during the propagation from PPD to us, basically ours, like the distance is more than 100 parsecs, so it's very long distance. So we expect axion affects photon and rotates its polarization plane. Every photon, all the photon gets their polarization planes gets rotated for the same degree.
For the same degree.
For the same degree, yes. Okay, for the same degree, we expect so because the size of this PPD is not so huge. So it's a 400 AU astronomical unit. So it's not so huge. And okay, in this mass region, let's say 10 to the minus 22 electron volt, so coherent size, the size of a coherent patch of the axion is more than about kilo parsec or like 1,000 parsec or something like that. So it's huge.
I see.
So you can consider this. So this entire PPD is inside one coherent patch of axion. So that's why we expect the effect are all the same.
Okay, yeah, that is an answer to my question.
Okay, good. Thank you.
Okay, so if there's no further question, then we now have 10-minute breaks, and the second talk will start 5:10 or 10:10 in European time. And we will have a 30-minute pre-discuss session after the second talk. And so you may use the time if you have further questions. And the talk files are uploaded in the Indico pages, so you may refer to it. So let us resume in 10 minutes, after 10 minutes.
Okay, thank you very much.
Yeah, thank you again to Tomohiro.
Thank you.
Hello, Rafael is there?
Hello, yes. Hi.
Hi, nice to meet you.
Nice meeting you too. Should I start sharing the screen?
Yeah. You may use the full screen mode. Yeah. Okay.
Yes.
And try to turn the page. Yeah.
Can you see it?
Yeah.
Okay, maybe
everything okay.
Okay, perfect. My connection is not great, so if anything happens during the talk, let me know and I'll turn off my video. I mean, of course, I'll keep sharing the slides.
So, can you turn off this button?
Which one?
In the bottom of the screen. Yeah.
Oh, sorry. Yeah, it will disappear. It will disappear automatically. Just we'll give it a second. Yeah.
Maybe yeah, just disappear. Okay, so let's just start the second session. So the second speaker is Rafael from IPHD. So he's going to talk about broadband detection of ultralight dark matter. So please.
Yeah, thank you very much for the invitation. Hopefully next time it's going to be in person. Yeah, so today we'll tell you about a new idea to detect axion dark matter, which I think has a lot of potential and can explore a vast parameter space that is now not being probed by any other experiment. And it shows some complementarity with the very interesting ideas that were discussed in the previous talk and also other ideas that are present in the literature. Well, I probably don't need to go through a very long introduction, but let me just spend 2 slides introducing the problem, even if probably you've seen duplications of this already multiple times. Well, as you know, the problem of detecting dark matter is very much open experimentally. You have about 80 orders of magnitude in mass that are variable, about 50 orders of magnitude in coupling of the dark matter to the standard model, which is actually not even a single direction, but it's a multidimensional space, plus another 50 orders of magnitude of coupling of the dark matter to itself. So hoping to cover this huge territory without any theoretical bias, I mean, is a bit optimistic in the best of cases, and certainly we cannot do it within our academic lifetimes, probably not also within the lifetimes of the children of our children. And so I'd rather try to identify some dark matter candidate that seems most promising theoretically and focus our effort first on these particles. And they probably don't need to convince this audience that axions are a very motivated dark matter candidate. They check all the boxes. They have a good UV motivation since they're generically predicted from string theory compactifications. They might, in some region of parameter space, solve another problem of the standard model Lagrangian, namely explain why the theta angle of QCD is so small. They're even appearing in multiple solutions to the hierarchy problem, not only the relaxation, but also other scenarios of cosmological explanations. And finally, they have a very simple and predictive cosmology. So if you go through this list, you'll see that it's not very different from what made weak interactive massive particles the favorite candidate of the particle physics community. And so as we spend a huge amount of intellectual, economical, and effective effort in detecting these dark matter candidates, I think we should do the same for the Axion, and actually we're just starting to do the same. The rest of the talk will be slowly building up to this next slide, where I give you a sneak preview of the sensitivity of our proposed apparatus. On the left-hand side, you can see what a resonant experiment can do. Actually, I'm a bit cheating because that's the full sensitivity with at very low masses is merging into the broadband sensitivity. And on the right-hand side, you can see what a broadband setup can do. By resonant and broadband, I mean that in one case, I'm going to scan a certain frequency in the experiment to match the axion mass point by point. And in the broadband case, instead, I'm making one single run with this frequency fixed at some value. And you can see that both ideas have a lot of potential. Of course, the resonant one is more sensitive point by point and can even get to the QCD line, which is this yellow line in my plots, for about a factor of 100 in axion mass. So there are 2 orders of magnitude of axion mass for which you can get to the QCD line. But the broadband setup, I would say, it's equally interesting for a number of reasons. Well, the main reason is that it's much simpler to operate. So if you build the same experiment, the natural first step is to run it into this mode of operation, which requires a much shorter time because you don't need to change the frequency point by point. Also, when the axion mass is smaller than the bandwidth of the resonator, it's actually a resonant experiment. So it's the same as the previous one. In fact, the 2 sensitivities are completely the same in this region at ultralight axion masses where the sensitivity is flat. And secondly, it's also technically less challenging because you don't need to control frequencies as precisely as in the resonant case. And the organizers have asked me to focus mostly on this broadband experiment, which I will do, but I will also spend a few slides on the resonance story. And so as you can see, in both cases, we can cover a large territory, going from axion masses a bit below a gigahertz, all the way down to the lightest viable dark matter masses, where the de Broglie wavelength of these guys is comparable to the size of a dwarf galaxy, and their occurrence time is extremely long. It's actually more than 10 times recorded human history. Okay, so this already gives you an idea of what I'm going to talk about next. And now let's step by step build up this idea. And I will start by explaining to you this blue line in the plot, which is a theoretical target. I mean, as you know, these targets are not that crucial. I mean, there are models which can populate most of this plane and give you axion dark matter, but they are more complicated. So it's nice to have a good idea of what are the simplest models that can populate this plane. And of course, one is the QCD line, the orange line. And I'm going to tell you what's the other one. So the other one comes purely from dark matter considerations. So we forget about coupling the axion to QCD. And we imagine that the axion is produced via the misalignment mechanism. For simplicity, let me say that PQ breaking happens before inflation so that I don't need to worry about other contributions to the axion relic density. But this is not crucial at all for the experiment. I mean, the experiment doesn't care how the axion is produced. It just cares that the axion is in the galaxy today and has the right relic density to be dark matter. Okay, so given this framework, if the axion were coupled to QCD, then it would have no potential at very high temperature. The potential then would be slowly turning on as you approach the QCD phase transition. Actually, not that slowly. Here I put a temperature to the 4th. In reality, more state-of-the-art calculations give a slightly different result, but it's just to give you an idea. It really doesn't matter for me how this potential turns on. And then finally, at a lower temperature, you're going to have the final 0 temperature form of the potential. And the point of this short slideshow is that in principle, the axion doesn't know anything about this potential at early times. So you generically expect it to live far away from its minimum. But I'm going to say more. Even if this potential existed from the beginning, which is what I'm going to assume for drawing this blue line, still the axion has no reason to start close to its minimum. So in general, you're going to have some energy density into this misalignment, which is going to be proportional to the axion mass and the scale of the potential, both squared. And I'm going to parameterize the misalignment in terms of this dimensionless parameter, theta bar. So if indeed most of the energy density of the axion is contained into this misalignment, then we can ask how the energy density evolves in the history of the universe. And you probably all already know that if you want the axion to be dark matter and extrapolate its number density way back, you're going to find a huge number of axion per de Broglie volume. So a classical description is appropriate, not to mention the fact that if the axion is produced in this way, it's also produced in a coherent state, which doesn't really matter, but it's even one more reason why these classical equations of motion are a good description. And again, you've probably all seen the equation of motion as well. It's just a damped harmonic oscillator with the damping term being proportional to the Hubble parameter. So the damping term is decreasing as the universe cools down and expands. And if you go ahead and try to solve these equations, there are two regimes. One where the axion is stuck and behaves like dark energy, when the second term in the potential is subleading, sorry, the second term in the equation of motion is subleading to the friction term. But then, as I said, as the universe cools down and expands, the friction term is going to decrease. And at some point, you're going to cross this threshold where the axion mass becomes larger than this Hubble parameter. Then the axion starts to oscillate, and it also starts to redshift like cold dark matter. So this is a simple story for how the axion might be produced and give you the observed relic density today. And if I imagine order 1 misalignment, so I'm not tuning anything, and I further imagine that the potential of this pseudoscalar exists from the beginning, so it's not turning on with QCD, then this defines my blue line. So I would say that this blue line is the simplest way to have axion-like dark matter if its potential doesn't come from QCD, but comes from some other sector that it's always cold compared to us. Of course, I could have drawn a million other targets. This is just to give you an idea of something, the most that is, in my view, as complementary as possible to the QCD line. All right, so after this longish introduction to the theory part of the plot, let me now turn to the experimental idea. And before jumping into it, let me tell you a few simple and well-known facts about axion dark matter. The first one is that to be viable today with these tiny masses, it has to be produced cold. Otherwise, it would be in contradiction with a host of astrophysical and cosmological observations. This cold particle that has essentially no kinetic energy, but just its rest mass as kinetic energy, will acquire a small velocity dispersion when it enters the galaxy, just from gravitational interactions. And this velocity dispersion is going to be of order 10 to the minus 3 the speed of light. So today there is a frequency spread, which is given by this velocity spread. And finally, as I anticipated before, the number of axion per de Broglie volume is really huge. Even within just the volume of a typical experiment of size a meter cube, the number of particles is gigantic. And the de Broglie wavelength at such low masses is even bigger than the size of a typical experiment. So this tells you that the axion looks like a classical field, which is approximately oscillating at the axion mass with some frequency spread. In practice, when you're looking at your apparatus inside the galaxy, all these axion particles have taken different paths to reach you. So you can imagine that there are many different wave packets that sum each other with different phases, because the phase in practice depends on the, say, cosmological history of this particle that has reached you today. And there is no reason why they should be coming all from the same direction or have all experienced the same gravitational interactions. So in reality, this axion field in your experiment is a Gaussian random field given by a sum over a huge number of plane waves. In practice, this doesn't matter that much because the frequency spread between these plane waves is very small. So you can use usual trigonometric identities and see that this sum factorizes into a piece that is oscillating fast, roughly at the axion mass. and then a sum of components that is oscillating very slowly with a frequency that is suppressed compared to the axion mass from this small velocity dispersion in the galaxy. So it's 1,000,000 times slower. So in practice, an effective description of this Gaussian random field is in terms of a monochromatic oscillation, so a very simple cosine of MA. And this description is valid for times that are 1,000,000 times longer than one oscillation period. So for reference, I'm putting here the typical numbers that you look for in a terrestrial cavity. So a micro EV axion corresponds to a gigahertz oscillation and a coherence time of a millisecond. And finally, also the spatial coherence of this field is very long compared to one over its oscillation frequency, again, due to this small dispersion velocity. So what's gonna set the spatial uniformity is the momentum this time, not the energy. And the momentum, since we're very non-relativistic, is going to be proportional to 1 power of this velocity dispersion. And so the spatial uniformity is roughly 1,000 of the inverse size that you expect from given a mass. And so again, this is good news for your experiment, because you have this coherent oscillation that persists over large distances and for a long time. In practice, when you go to very low axion masses, there are some statistical subtleties to take into account when you include the amplitude in your calculation, but I'm not going to talk about them today. I mean, they changed the reach by factors of a few, but we included them properly by doing a fully LHC test statistic type thing with nuisance parameters, et cetera, et cetera. So if you're interested in the technical details, I'm happy to talk more about them, but if not, you can just imagine that the axion is this simple monochromatic field with a fixed amplitude given by the dark matter energy density and a fixed frequency given by the axion mass, with a small shift because, again, I'm in this very simple illustrative slide, I'm neglecting the fact that the sun and the Earth move relative to each other and the sun moves relative to the galaxy. So there is not only this velocity dispersion, but there is also a component that gives the axion a tiny kinetic energy. But again, for every practical purpose moving on, this doesn't matter that much. So this is the simple intuitive picture that one should have of axion dark matter in the lab today. And if you have this picture, then the first idea that you might have, which was already explored in a very different and creative way by the previous speaker, is to write down Maxwell's equation. Because if you have a coherent classical field, you might want to try to detect it using other coherent classical fields that you know how to manipulate well in the laboratory. And these are electromagnetic fields. And so the very first step of most axion detection proposals is to write down the modified equations of electrodynamics in the presence of an axion field. And if you neglect the small axion velocity today, then the leading effect is this one. So there is a source term that in the presence of a background magnetic field looks like an oscillating current. And this current, again, is oscillating at the axion mass, depends on the axion coupling to 2 photons and on the dark matter energy density today. Just to give you an idea of the size of the currents that we're trying to detect, we can compare this current on the QCD line for a largish magnetic field of order 4 Tesla with the currents that you can have at home. So your copper conductor in your walls giving light through your light bulbs can support a current of order 10 to the 7 ampere per centimeter squared. Of course, this ampere per centimeter squared doesn't tell me anything because I always work in natural units, but you can just compare the two numbers and see that this current given by the axion is some 22 orders of magnitude smaller than this. So it's very hard to imagine that you're going to have an instrument that is sensitive enough to just pick up this current as it is. And so again, first natural option that's open to you is to try to resonate and build up this current until it becomes detectable. And indeed, this was one of the first and most successful ideas for the detection of axion dark matter that led to the development of ADMX. And the idea is very simple, and it's going to be similar to what we do as well. You just impose boundary conditions on the photon. So you build a box of a conductor. This breaks translational invariance, and so it's giving a mass to the photon inside the cavity in some sense. The more traditional way to see this, I mean, the non-particle physicist way to see this, is that the cavity has normal modes. So you can decompose the electric field inside the cavity as a sum over these normal modes, as I did in the slide. And each one of these normal modes approximately reacts as an harmonic oscillator, with the damping term fixed by the quality factor of the mode, which depends on how much the electric field penetrates the walls. So how bad of a, I mean, how non-ideal your conductor is. And of course, this Q factor can be different for different modes because each one has a different profile in the cavity. And so some of them can be closer, concentrated closer to the wall, other ones can be more in the middle, etc., etc. And actually, most of the research in these cavities goes in the direction of building weird corrugated walls that concentrate the mode in the middle so that the quality factor becomes higher. But anyway, so setting these technicalities aside, now you have a sum over harmonic oscillators that is excited by your axion current. And the first thing that people did was to imagine turning on a very big static magnetic field. So to try to maximize the amplitude of this right-hand side of the equation. And if you do that, you're forced to choose one normal mode of the cavity to match the axion mass if you want to resonate and build up power. And so in the end, you're going to have an electric field in the cavity, which depends on two time derivatives of the axion. So one of them is going to cancel the MA that we put in the amplitude to reproduce the right dark matter energy density, but the other one sits there. So as you go to lower masses, the power available to your experiment is going to decrease. And this idea, as I said a few slides ago, is extremely powerful and led to ADMX and other successes. And the reason is that if the axion mass is a microelectron volt, so oscillates roughly at a gigahertz, then technology is on your side. So we know how to build these cavities of order 10 centimeters or more very well. We know how to build electronics also very well at these frequencies. We can essentially hit the quantum limit now for amplifiers. And so if you take this box, you put it in a big magnetic field, you're going to be very sensitive to masses around this value. However, the moment you want to go lower in mass, as we tried to do, you encounter two problems. The first one is the second one is the one I anticipated, that your electric field and hence your power is proportional to the axion mass. So you have less and less power as you go lower. And the second one is that you need to build a bigger and bigger cavity as the axion mass decreases, because you're matching the resonant frequency of the cavity to the axion mass, and the size of the cavity goes like 1 over the typical resonant frequency. So to solve this problem, we proposed a very simple alternative to this traditional scenario, where instead of building that cavity that's the size of the axion mass, you build a cavity of fixed size, but you tune it in such a way that there are two nearby modes. One mode at omega 0, I'm going to call it the pump mode, and one mode at omega 1 that I'm going to call the signal mode. And the split in between these two modes is going to be tuned to the axion mass in the resonant case. So that if you put electromagnetic energy into the lower mode, the pump mode, then an axion dark matter field coming in is going to convert photons from one to the other. Of course, it's also important that the two electric fields of the two modes are perpendicular so that you maximize the geometric overlap with what the axion wants to do. So the axion couples to E dot B, so you want the two electric fields to be perpendicular. And so you see that conceptually, it's a very small step beyond what was already on the market. But this gives big parametric advantages for signal power at lower axion masses that I'm going to explain in a second. And this was originally proposed by me and Slack collaborators in a paper 2 years ago. And as I said, the idea is not that different from the usual ADMX story. So in the usual ADMX story, you have a big static magnetic field, and you're exciting a signal that is oscillating at the axion mass. In our story, you have a oscillating magnetic field at a large frequency, omega-0, and you're exciting a signal again at a large frequency split by a small amount from the original one. To be fair, this is not a completely new idea. So the way I came up with this simple mechanism to detect axion dark matter was by reading the papers of my great advisor, whom in the 80s had proposed a similar setup to detect gravitational waves. So again, you have this, you build this cavity in such a way that there is a small splitting between these two modes, and then the gravity wave is deforming the boundaries of the cavity in such a way that photons in the lower mode get bumped up into photons in the higher mode. So it's almost the same idea. The main difference is that in their case, they need the mechanical resonance. So they, in reality, have a graviton mixing with a phonon that's exciting a resonant mode of the cavity, which then is mixing the two photons. In our case, instead, we have this direct coupling between the axion and the two photons. But the moment I try to draw a particle physicist diagram for this experiment, I immediately could see that the axion could do the same thing. But aside from this historical curiosity of how the idea was born, the really important point about this slide is that these guys actually built an experiment, or at least a prototype, in 2005. So a lot of our noise estimates come from experimental measurements that they made back then. All right, and another interesting point, which is slightly outside of the main line of the talk, is that today actually SRF cavities, so superconducting radiofrequency cavities, as the one that we want to use for this experiment, and as the ones that they were proposed for gravitational waves, are actually becoming increasingly more important for fundamental physics. So until a few years ago, they were mostly used to accelerate particles. And so all the colliders that you know and love make use of these cavities. However, we recently realized that they can also be used as a precision instrument, mainly because their quality factor is gigantic, order 10 to the 11 or above. So they're very, very close to being an ideal harmonic oscillator. And there are other interesting proposals in the literature to use them to detect other stuff, either axions, again, in different regimes, or milli-charged particles, or dark photons. But this list here is very non-comprehensive. So I'm hoping that the moment that one of these efforts goes from prototype or idea to actual experiment, then it can be used for multiple new physics searches. All right, so now I've given you the basic building blocks of the idea, but I haven't yet told you why it improves the sensitivity at low axion masses. And there are essentially two simple reasons. The first one is that if you replace a static magnetic field with an oscillating magnetic field as your signal source, then the first time derivative, it's hitting the magnetic field, which is oscillating at a large frequency compared to the axion mass. So if you just compare side by side the electric field that you get in a static experiment versus the electric field that you get in our experiment, you get a big enhancement of order omega-0 over ma. And this enhancement becomes bigger and bigger as you go to lower axion masses. So this is the first simple reason why you're gaining something. The second one is that there are two time scales in the experiments. There is the axion coherence time, so this axion quality factor for the 10 to the 6 given by the velocity dispersion in the galaxy over the axion mass. And then there is a characteristic timescale associated to dissipation in the resonator. So at some point after a time q over omega, you stop increasing signal power. So you reach a state of equilibrium in your resonator where dissipations and the power you put in become equal. And so whichever of these two things happens first determines the maximum signal power that you can have in your experiment. If you take the resonant frequency to be the same as the axion mass, you see immediately from this equation at the top of the page that what matters is the minimum quality factor. So there is no point in building a resonator with high Q. And that's why, for example, ADMX has a Q of order 10 to the 4, if I remember correctly. But anyway, it doesn't go beyond the Axion quality factor. Instead, if your resonance frequency is much larger than MA, then you have a lot to gain in going to higher quality factors, because you can saturate this resonator power much later. So you want to build higher Q resonators. There are also other reasons due to more technical subtleties that Peter Graham and collaborators explained in detail in another paper on axion dark matter detection about overcoupling, et cetera, where large Q can be beneficial for other reasons, which we use as well, but I'm not going to go into those details. So, okay, so now you have also an idea of why you might expect a good sensitivity at low axion masses. Of course, you might have already guessed that this doesn't come for free. So greater signal power comes with greater noise sources, because we're putting a big oscillating electromagnetic field inside our pristine cavity that's supposed to be sensitive to tiny axion effects. And indeed, in a couple of slides, I'm going to tell you more about the noise. But before that, let me tell you how this broadband setup operates. In the case of the resonant one, it's totally straightforward. We have these two modes, and then you change a bit the cavity size by pressing on one side so that you scan the splitting between these two modes, and at every axion mass, you fix the frequency of the signal mode to be frequency of the pump mode plus the axion mass. In the broadband case, instead, we keep the two frequencies fixed. And we decided to keep them fixed and essentially degenerate. So we want them to be the same within the resonator bandwidth. And as I told you before, these quality factors are huge. So order 10 to the 10, 10 to the 11. So these two frequencies are really degenerate. The reason why we keep them degenerate within the bandwidth is that in doing so, for every axion mass below this bandwidth, so roughly 10 to the minus 17, 10 to the minus 18 EV, you get the same sensitivity as a resonant experiment, because everything is within the bandwidth, and so you are still resonating, and your electric field is enhanced by the quality factor of the cavity, if you can saturate it. And typically, you can saturate it because of these masses. The axion clearance time is extremely long. Then, okay, originally we thought that that was it. I mean, that we would have sensitivity only there. But it turns out that we just run our code to higher frequencies. And since the noise sources are also very far off resonance, not only the signal, you still retain very good sensitivity all the way up to essentially whatever mass you like. We cut the plot because at some point the two modes are not almost at some point the splitting becomes too big, and I'll explain it to you later if you ask. But well, the only slightly subtle point here is that we're still keeping the two frequencies fixed. So the signal mode, let's call it, and the pump mode are still degenerate essentially in frequency. But now we are reading out also other frequencies. So the experiment is always the same, but our data acquisition stream is reading out many frequencies, including the much higher ones where the axion lives. So our actual signal frequency, omega sig, let's call it, is going to be much bigger than the frequency of the signal mode. So that's why I'm saying that we're driving it far off resonance. But the same is going to be true also for noise. All right, so this gives you a very, very rough snapshot for why the experiment works. And now let me tell you a bit more about noise sources and what's our expected sensitivity, both with some nominal choices of parameters for noise and some choices that are orders of magnitude worse than the state of the art. All right, so schematically, we have the following noise sources. So we have thermal noise like everyone else, both in the cavity and in the readout system. Then, since we're turning off a big oscillating electric field in the cavity, we also have field emission. So there can be electrons that are stripped off the walls and then radiate photons inside your cavity and populate the signal mode. In reality, this effect is very small because the electrons that are produced this way are relativistic, and so they're emitting over a spectrum of order electron mass, so of order 10 to the 6 electron volts. But the width of our signal mode is roughly 10 to the minus 6 electron volts divided by 10 to the 11. So already just this naive kinematical overlap is tiny. And then there are also other effects. I mean, these photons are emitted all over the place, but the electric field direction of the signal mode is fixed. And so there are a series of suppression that make this effect under control. Then, compared to more traditional setups for axion detection, we have two additional sources of noise. That coming from the vibration of the walls, which was the signal for the gravity wave people that I talked about a few slides ago, where a phonon is mixing two photons essentially and bumping up the photons in the pump mode to the signal mode. And finally, there is the noise that we ourselves are putting in the cavity, because there will be some leakage from the energy that we put in the lower line mode into the signal mode. And let me start with these sorts of noise, which is the most important one at very low masses. And it's also the most irreducible one. So the way we parameterized it is quite simple. So we looked online for what oscillators exist, and we took one of the spectra. So the spectra that we're using in our calculation is that of an oscillator that you can buy today. It costs, I think, order $10,000. It's nothing super fancy. And has some frequency tail. So if the oscillator was perfectly monochromatic, we would not have this problem. But of course, there is no such a thing as a perfectly monochromatic oscillator. So the first ingredient to compute these sorts of noise is the spectral shape. So how power is distributed in frequency space. And this is this S sub phi that I've circled in orange in the phase noise expression. And this, as I said, we took it just from a commercially available oscillator. Then there is the response of the cavity. So you're just, again, solving an harmonic oscillator equation. So you have something that looks like a bright Wigner here in blue. And finally, there is the most important parameter, which is the one that this Italian collaboration measured, which is essentially the geometric overlap between the two modes. So if you imagine that you're loading the cavity by coupling a waveguide geometrically just to the pump mode, essentially you choose a direction for the electric field in the loader and match it to the direction of the electric field in your pump mode, then you can highly suppress the amount of energy that goes in your signal mode. And the number that these guys measured 15 years ago was 10 to the minus 7. So already a huge suppression in amplitude, which then enters squared in the power, so 10 to the minus 14. And this might seem a large number, but in reality, for us, it's a conservative estimate, because we're taking it, again, from this gravitational wave experiment. And for them, the two modes are parallel. They're just oscillating differently in the two twin cavities that they're using. While in our case, the two modes are perpendicular. So in reality, the first term in perturbation theory vanishes for this reason. So we could have been more aggressive, but we decided not to be. And we're showing our most aggressive sensitivity curves for this number that was measured 15 years ago. And then we also degrade it by a lot. I'll show you in a second. The second source of noise that's important is mechanical noise. However, is much, much less important than what you're familiar with from interferometers, if you ever thought about LIGO or similar things. The reason is that the cavity walls are rigid, so their typical resonant frequencies are never below a kilohertz. Actually, this is another thing that this Italian group measured. And so it means that for a low frequency perturbation, it's pretty hard to deform this cavity. And so this is the very basic intuitive picture for why vibrational noise is not a huge deal for us at low masses. But to be a bit more precise, again, you're just solving harmonic oscillators equations. So you have a bunch of bright Wigners in your final expression. And the key quantities are, again, this epsilon parameter, because you are still imagining of moving photons from the pump mode to the signal mode. So you're not moving all these photons, but only the ones that are accidentally aligned with the signal mode. So again, there is this geometric suppression in the same way as there was for the previous source of noise. And then there is how well you can attenuate vibrations, which is parameterized by this S of Q, which is essentially the power spectral density of wall displacements. And to determine this number, we used force power spectra that, again, this Italian collaboration measured down to a kilohertz. And then we are using the attenuation that was achieved at Fermilab recently by the Dark SRF collaboration. So they measure frequencies, but frequencies essentially are how much the frequency of the cavity changes is just proportional to how much the wall is deformed. So from this, we can get an attenuation number over the force spectra measured by the Italian collaboration. And combining all these ingredients, we get an estimate for mechanical noise. And we check that at very, very low frequency, this estimate is conservative compared to what you would expect from ambient noise. So we took the spectra of seismic noise measured by different seismometers around the world. And we see that instead, the dominant source of vibrations for this collaboration was coming from something inside the laboratory. So it was probably the cooling system. So our estimates are very conservative compared to what you just expect from the ground vibrating or the density of the air changing, et cetera, et cetera. Okay, so I spent a couple of slides trying to convince you that I'm being conservative using rough physics arguments. Indeed, I mean, you can read the paper and we've been more precise. This was just to give you an idea during the talk. But if you don't believe me, I'm not offended. You don't need to believe me because this experiment retains a lot of sensitivity, even if you degrade by orders and orders of magnitude the parameters that we think are today's state of the art. So let's look first at the broadband sensitivity that I showed you a few times. So the light green area, the one that covers the most territory, corresponds to a 5-year experiment with a epsilon geometric parameter of 10 to the minus 7, so what was measured 15 years ago, and a quality factor of 10 to the 12, which is a factor of a few bigger than the quality factors that have been achieved about a few years ago. So it's being slightly aggressive only in the quality factor, but let me be completely conservative. So let me run my experiment for 10 days, have a quality factor of 10 to the 10, which was what was available again 15 years ago, and use a epsilon parameter, which is a 100 times worse than the state of the art. Then I still cover new territory. Even if I run my experiment just for 1 day with the same 15-year ago quality factor, and I even imagine that I don't know my geometry even at the millimeter level, which is a bit crazy even for cavities that are built for accelerators, then I still cover new territory. And I could do the same exact exercise for the resonant case, which you might be more interested in since it gets to the QCD line. Again, if I use this epsilon parameter measured 15 years ago and a quality factor just a factors of a few above the state of the art, I get this full dark blue sensitivity. If I degrade the quality factor and the epsilon parameter to what was not, I mean, what was that could be considered pretty bad even 15 years ago, I still get to the QCD line, at least for a factor of 10 in axion mass, and cover a broad parameter space that's still unexplored. And I can keep going, getting things worse. Here, I'm just degrading a lot this geometric control that I have of the cavity, all the way down to imagine that I don't even know the size of my cavity within 10%. So totally crazy, I would say. But still, the experiment can cover new territory. This is the worst reach curve that you see in this plot for the resonant case. Again, for the resonant case, you might want to tell me that I don't know anything about ground vibration, so I completely screw up my calculation, and I would tell you that it doesn't matter, because even if my walls move a factor of about 10 to the 5 more than what has been shown to be possible at the dark SRF experiment at Fermilab. Still, I keep all my sensitivity on the QCD line. The only thing that I cannot do anymore in this resonance setup is to go to very low frequencies, because at that point, I don't know the frequencies well enough. They're just jittering too much to resonate. But this is not a problem for the broadband experiment, for example, and I'll show you in a second. So now, again, let me do the same exercise for the broadband case, and roughly in the same steps. So let's say that I have no control of the geometry of the cavity. I've kind of already showed you what happens here. Sure, the sensitivity is very degraded, but we still cover a lot of new parameter space over a wide range of axion masses and couplings. Again, I can imagine that for some reason I missed some low frequency noise sorts in my calculation. And what happens if I degrade by factors of 10 or 100 the width of the oscillator that I'm using to load the cavity, which is an effective measure of low frequency noise, then I lose sensitivity mostly at intermediate masses. This is also telling you that vibrations matter at these intermediate masses, say between 10 to the minus 18 and 10 to the minus 12 EV, but they don't matter at the very lowest masses. So your intuition might be that the lower you go in frequency, the worse vibrations are. In our case, in practice, it's not really true, mostly because the noise from the energy that we already put in the cavity is so overwhelming that in this flat region at the end of the plot, all that matters is how well you can reject it. You're just already putting a lot of electromagnetic energy. So it's just that another background is dominating. Okay, and finally, again, I'm going to imagine that I don't know how much my walls vibrate by a factor of 10 to the 4 watts than what can be achieved already. And again, the sensitivity is degraded, but we can explore a lot of new parameter space. So all of this was to tell you that even if this idea is at the level of a theoretical proposal for the moment, which of course we did in conjunction with experimentalists to be realistic, but still I think it's very robust to potential sources of noise that we have not considered. Yeah, so these were my propaganda slides, let's say. So finally, I think that these dark matter candidates that look like classical fields and that pseudo-Goldstone boson couplings to the standard model are strongly motivated theoretically from a host of considerations that I made at the beginning. And I think they have all the qualities to become the new WIMP. They probably already are. The main difference between them and the WIMP is that experimentally, the territory is much more open. So we've seen very interesting ideas in the previous talk. There are more ideas in the literature that are being proposed. And so I think that we are kind of at the beginning of this field. So it's the moment where you can have a creative idea and then bring it all the way to a functioning experiment that can cover new parameter space. And this excites me, and hopefully we'll reap the fruits of these initial proposals in the next 5 to 10 years, and we'll cover almost all viable axion dark matter parameter space. Maybe almost all is optimistic because getting to the QCD line at very low masses, it's hard, but there are proposals like Casper. And I think that this idea that I showed you is a good bridge between the ideas at high masses and the ideas at the lowest masses. And thank you. That's all I wanted to say.
Thank you very much, Rafael. So questions?
Oh, sorry.
Go on.
Hi, Rafael. I want to ask you if you have an idea in the resonant case on how much time it will take to scan the QCD axion part.
Yes. So so to be consistent, I mean, so we wanted to make the propaganda plot against, I mean, us versus DM radio, which is, I think, what Abracadabra now has become as well. So this one. And so we essentially chosen the same integration time. So for us, 1 e-fold is 1 year. And so if you want to scan, say, a factor of 10 in mass, it's about 3 years. So if you build a single cavity, it's going to take 6 years to cover the factor of 100 QCD mass in QCD on the QCD lab. I think it would be more doable technically to build 2 cavities. Can you hear me?
Yes.
Clear? I think I might have frozen for a second. Yeah, so I was saying that if you build 1 cavity, it takes about 6 years. But I think if you build 2 cavities, which would be more feasible experimentally, because we know the resonant. So I should say that what makes a resonant experiment hard is scanning, in the sense that we know very well how to scan for about a megahertz, let's say, because you can push on the wall of the cavity using a piezoelectric sensor. And so this would cover roughly one half of this QCD line parameter space. But then if you want to scan in bigger steps, then you need to build a cavity like this one, where there are some fins at the bottom that you put in and out. So these cavities are what our experimental colleagues imagine to be possible. But of course, in this case, it's harder to characterize them. There are these potentially sharp edges that create new backgrounds. So my ideal picture is that we're going to build 2 cavities to scan the QCD line, both smooth. And the way we do the scanning is by pushing on the bottom of each cavity with a piezoelectric sensor. And each one is centered at a different splitting between the 2 modes. And in this case, okay, to take double the money, but half the time, so 3 years.
Okay, thanks.
No problem. That's also why I like the broadband case, because in the broadband case, you build 1 cavity, you explore all the space. That's it. No problem with scanning whatsoever. Let me stress that I think it's doable to do the scanning. Otherwise, I wouldn't be making these plots. And we had many conversations with our experimentalist friends on the resonant case. But to me, this is the most challenging aspect of the experiment.
So from the experimental point of view, people started building this, or still?
Well, so the guys in the original proposal are of course interested, and they have some cavities lying around that could be used to characterize the noise, but we have not yet found a founding source and an actual way to build the prototype. So we are still looking for experimental PIs. So if you know of someone interested, we're takers.
But because the smallest version, it seems pretty cheap from what I understand.
Yeah. I mean, you build a standard SRF cavity, and that's it. I mean, you do your broadband thing. You just have to manufacture it in a specific way. But yeah, it's super standard and very easy to do. I mean, the non-easy part is that you want high quality factors. So it has to be a high quality cavity, but these already exist. So actually, the real candidates to do this out of the box are this Fermilab group, these dark SRF people. They essentially already have the cavity. At least they have a cavity that is very similar. I don't know if they have these 2 modes with the right spatial orientation, but I mean, they could build another one and run our experiment. So we are in contact with them as well. We'll see how it goes. What's really stopping us is that now all SRF people in the US are busy with projects that have been going on for 10 years, like the electron laser at SLAC, other stuff at Fermilab. So they have to finish that stuff that's paying their salary, and then they can focus on new physics searches.
Sorry, so one thing I didn't exactly understand was your statements about this sort of being invented originally for gravitational waves, or based on the same techniques. And my question is, I mean, we sort of did something similar with interaction of axion neutron. Can you just use data that was taken for this something completely different and then calculate some, first bounds from that, which would be not projections, but actual bounds that might not be optimized because they didn't do everything you might want to do? I mean, just convert data that was used for something else.
So if you're, let me say that, so this idea, I mean, of frequency conversion essentially has been existing forever. So I used the example of the gravity wave people because that's how I personally got the idea. But in reality, there are many proposals along this direction. There was also a similar proposal by CTPU that I discovered after writing the paper of doing this for IMAS actions for some reason. And in general, I mean, again, frequency conversion is used all over the place, also in signal processing, et cetera, et cetera. Concerning what you propose of getting a bound from existing data, I mean, I don't think you can do it from SRF cavities. Maybe you have in mind some astrophysical process, though. What were you thinking about?
No, I just didn't understand. No, I was just saying, I started with, I didn't exactly understand what you said about the gravitational waves. So, like, whether their detectors are exactly what you wanted to have. I was saying.
No. I mean, well, there is the modes are different because they want to, they are building something that it's optimal for a quadrupolar interaction of the gravity wave, which couples to FF, not to FF dual. So already the overlap for us, it's almost zero. But also the data taking that they've done, I think it was not enough for a physics run. They just measured the noise. So they just did measurements to characterize this geometric suppression factor, et cetera, et cetera.
So no one actually built this yet and ran it.
Yeah, exactly. But in principle, the gravity wave thing exists. So if you want to do it for gravity waves, you should go to CERN and find this prototype somewhere and plug it in and see what happens. Because I think they didn't do a physics run for reasons that I don't really know.
I see.
Hi, thank you for the nice talk. So I have a question related to the readout noise. So I noticed in your setup, the temperature is 2K, right?
Yes.
So it's higher than H omega. So I'm not sure in this case if it's non-trivial to achieve the standard quantum limits for the readout noise. So. Yeah,
so in that we are borrowing results from other proposals where they are trying to do the same and decoupling the amplifier enough that I mean, so the amplifier can be very cold in some, let's say very pictorially, as far as I understand, and then your cavity can be hotter. So for me, the quantum limit is just in the amplifier. So indeed, we do include the thermal noise. What's quantum limited is just the amplifier.
Okay. So I have another question, which is, I think your signal to noise ratio is inverse proportional to the square root of time, right? So I think that's only for the Gaussian noise. And in your setup, I think there include a lot of other, some noises, which I'm not sure they are Gaussian, like the mechanical one.
They are okay. As far as we understand, they are all Gaussian.
Okay.
They essentially, they're all coming from this tail of the oscillator mostly, which behaves as a Gaussian source of noise. I mean, it is colored noise. It's not white noise, but it's colored and Gaussian. Okay. We did write down a line. I don't know. I probably don't have it in the backup, but yeah.
Okay, thank you.
No problem.
So Raphael, I have a question. So in your plot, I see the sharp upper bound on the axion mass that can be proved, like 10 to the minus 6 electron I mean, your sensitivity, here.
Yes.
It's around 10 to the minus 7. But in principle, I guess that if the cavity size is small, then it can be very rigid to 10 to the minus 5. Why there's a sharp cutoff?
Yeah, so we did that just because we wanted to show the sensitivity, let's say, the expected sensitivity for a single cavity. So, for example, in the resonant case, we cut our reach when the two modes were split by order 1. So at that point, essentially, you don't have any more two modes that are close to each other and separate from all the others, but you have a bunch of modes that are all at the same distance from each other. So essentially, our theoretical treatment is breaking down. Of course, you can build, as you said, a smaller cavity and essentially extrapolate by eye this reach along the line that you see, because there all it matters is thermal noise. The reason why we didn't do it is because essentially where we cut off our sensitivity is where ADMX is supposed to get to the QCD line already. So we trust that ADMX is going to be able to do that, and we didn't find a good reason to try to compete. But in principle, we can. The only problem is that if you do that, I mean, if let's say you want to build one cavity that gets to higher masses, then your sensitivity is great at low masses because the signal power goes like 1 over the frequency of the signal mode when the axion is very, very narrow. So this is the logic. Essentially, it's a trade-off between how much sensitivity you have at lower masses and at higher masses. So in principle, you can build two cavities if you have the money and be sensitive to both mass ranges.
Another question is, so
sorry, I don't know if I froze because I keep seeing on my screen your connection is unstable.
my connection is not good.
Yeah, but if you were,
maybe it's better now.
Now it's okay. It just happens.
Okay. So I have a second question. So for smaller axion mass, you have to fine tune the cavity size very finely, right? To obtain the resonant mode.
Yes. So in reality, when you see this resonant, so this sensitivity on the left, it's resonant down to roughly 1 Hertz, and then it's the same as what I'm showing for the well, no, maybe a bit below 1 Hertz, maybe down to 0.1 Hertz, and then after that, it's the broadband sensitivity. So essentially, with current technology, we know how to scan frequency splitting at the level of 0.1 Hertz.
Oh, actually, my original question is, so I naively guessed that the noise will be increasing for smaller axion mass, but here, starting from the 10 to the minus 7, the upper bound, it shows that it tends to increase the sensitivity for smaller axion mass.
Yes. Let's see. Maybe I do have. Let me see if I have a plot of the noise in the backup. I mean, indeed. So as you can see in the left-hand side, where the sensitivity is increasing is where your thermal noise is limited. So in that region, the shape of your noise in frequency space is flat, but your signal power is improving. That's what's happening. And then this phase noise and mechanical noise start becoming dominant, and then your sensitivity decreases. So maybe I do have a plot, maybe not. Let me see. Yeah, so maybe this one is the good one. So indeed, the noise increases at low axion masses, but it takes a while before these sources of noise take over the flat ones, just because of this geometric suppression in the end, and because of the bright linear suppression coming from the high quality factor. So you can imagine very roughly that the sources of noise are localized at the same frequency as the pump mode. So you are many widths away from the signal mode. And of course, as you decrease the axion mass, these two frequencies are coming closer together. And so at some point, these sources of noise dominate. But given that they are very suppressed geometrically, they start dominating only below, say, 10 to the minus 13 eV. It depends on the plot. I mean, now I'm showing you two panels with different choices of parameters.
Okay.
This is the rough picture. And well, this discontinuity in the mechanical case is because there are resonant modes of the cavity down to a kilohertz, but not below, because the cavity is too rigid to resonate below a kilohertz. So mechanical noise is maximally bad, meaning it grows very fast as you decrease the axion mass when you have a resonance, but then it starts growing more slowly. It's again, essentially becomes just a Breit-Wigner.
Yeah.
I don't know if this is fully answering your question or not.
Yeah, I just roughly understood.
Yeah, it would require also looking at how the signal power goes, which I don't know if I've written it anywhere. So I had an expression somewhere, but it was, I think, a bit misleading because it was highlighting some other aspect of the signal power and not the one relevant to this case. But let's see. So when the axion is broad, so in this region where you see the sensitivity improving, the signal power is dominated by the axion time scale, essentially, so Q over MA. And so if you divide this energy by this time to get a power, you get something that goes like 1 over MA. So long as the axion is the one associated to the shortest time scale, as the axion becomes narrower, your signal power is increasing. I don't know if it's super intuitive. It is a little bit, because you have power that is, you have to imagine that you have the bandwidth of your oscillator, which is some fixed box. And then axion signal being much broader than this box. And then as you go to lower axion masses, this broad peak is getting narrower and narrower. So you get more and more power inside the box. And so that's why in that region, the signal power appears to be increasing as you go down in axion mass. And since the noise is flat, then the sensitivity improves. So this is the full story.
Thank you.
No problem.
Further questions? If not, then let's thank to Rafael again. And so officially today's session is over, but if you have a further question, then you may ask to also. So Tomohiro is still there. So yeah, so now it's a pre-discussion session is open for a few minutes if there are further questions. But I see there's no, it doesn't seem to be the case. So maybe, yeah, so today, let me close the session and we may see you tomorrow. Thank you. Thank you. Goodbye.
Bye-bye. Thank you very much again for the invitation.
Bye. Thank you.